hope I'm audible. Right? Yeah, yes, my microphone is on. Then let's start session 1. So it is again the session name itself is nanomaterials and their properties. So we'll deal with the nanomaterials and what are the different types of nanomaterials, what exactly are nanomaterials. Then we dwell into their properties. After that, and if time resumes, then we will even discuss some characterization techniques which are used to like know about the nanomaterials, right? Yeah, so it totally depends upon how many sessions the speaker is going to take, right? So it is rerun, so let's see if any extra session is there, then in extra session I might give some time for the characterization techniques, and yeah, that's all. So let's start now. So sir has discussed, like gave a brief introduction on what. So in first lecture we can see it is mostly about the coursework. So which is not important to you because the coursework is related to the IITK students. So it is related to the IITK students. So half of the lecture is totally on the like marks, everything. So which is not for you actually. Then after that the sir discussed about like what are the nanomaterials, right? So I mean, there was huge surge from 2010 or 2012 of nanomaterials, right? This nano names, this nano name, you can see it everywhere, right? Even caves, nano cave, nano hub, and you can just go through it, right? So nano is a fancy name. So what exactly is nano? So in terms of like length, you call it 1 nanometer equals to 10 to the power of minus 9 meters. Right, so this is based on dimensionality. Now coming to nano, right? So you can even have seen this micrometer, right? So using 1 micrometer equals to 10 to the power of minus 6 meters, right? So again, we have different names, right? So but you still see nano mostly, right? Why? Because the nano name itself is quite fancy. You can use it anywhere and you can look good, right? You do not see people using the micro or milli. You don't see those names. You can see just nano. Right? Yeah, its name itself suggests it's good. Now, coming to the scientific part, that is the philosophical part, right? So coming to the scientific part, now, as I have said before, 1 nanometer equals to 10 to the power of minus 9 meters. So you have meter, then you go centimeter, then you have millimeter, and then again you will have micrometer or microns, then you have nanometer, and then you have angstroms, and then you have picometers, right? So we take meter as an SI unit for most of the cases. So yeah, you can take it. It depends on you, whatever unit you are going to take. But to have some reference, right? So for reference itself, we are taking meter as a reference scale. For everything else, you can take kilometer itself also. But when you take kilometer, the value becomes so big, it will not be like sensical, right? It doesn't make any sense when you try to pronounce it or say it. So it's better to use meter because when you say nanometer, the meter itself is there. So that's why our meter is our reference scale. So wherever you go, wherever you go not. So wherever in these sessions, I will just take my meter as a reference scale. So yeah. Now I will just mention it here. Our meter is our reference scale. In all sessions, right? So meter is our reference scale in all sessions. So now you say the nanoscale, right? So these all books are taken from one book. Whatever I say, whatever I'm going to teach you, they are all taken from only one book. It's Michael F. Ashby. So that is like I won't say the holy grail for nanomaterials, but it's like more introductory to nanomaterials. So you can just have everything there, right? From introductory part to what are the phenomena that are happening because of the nanomaterials. So what exactly are nanomaterials? What are different types? So how do you prepare nanomaterials, nanomaterial making techniques, and also now how do you measure the nanomaterials? Like how do you see the nanomaterials? So those will be from the characterization techniques. So yeah, it will have everything. So please refer if you have any, like if you want to go deep into it, you want to understand every how do you say, every grain of it, then you should like please visit it at least. You can see it, and some explanations are very well explained in there. Some explanations are very hard. You can just go for Wikipedia, or you can just search for ChatGPT for like simple explanation, right? It's on you. So what you want to do, right? Yeah. So nanoscale. I mean, let's see how do we characterize the nanomaterials, right? We have zero-dimensional nanomaterials, then I have one-dimensional, and then two-dimensional nanomaterials, then finally three-dimensional nanomaterials. See, during explanation this, I will also clarify. I will also introduce questions, right? So it is more likely the main objective of these sessions are like to help you in solving the questions. So I will make sure include questions such that you can easily answer them in your like what do you call the week one worksheet, or assignment problems, or worksheet, or exam one. For even exams, you can just refer to these sessions. You will understand, right? Yeah. So 0D, 1D, 2D, and 3D. Now again, we have one more slide. Yeah. See, what do I mean by zero-dimensional? So this is one thing. One-dimensional nanomaterials, two-dimensional nanomaterials, and three-dimensional nanomaterials, right? So we know every shape is in 3 dimensions, right? So for basic understanding, let's not move on to the higher dimensions. So let's stick to up to 3 dimensions, like the length, breadth, and height. Let me mention it here. So we all are well versed with our coordinate axis, which is x, y, and z. So any, how do you call, any object in universe should occupy some space, right? or we might call it empty space, so which shouldn't be. So any object in universe should occupy some space, and that space should be 3 dimension, right? Until or unless it's not 3 dimension, you can touch or feel anything. So you cannot touch anything if it is not in 3 dimension, right? It should have 3 dimensions, then only you can touch it, or at least you can see it, right? Now one dimension is nothing but let's say only one dimension is not in nanoscale. So 3 dimensions means all 3 dimensions are not in nanoscale. So again, I have to define my scale first, right? So my nanoscale is defined as whatever whatever the object is, if one of its dimension is lying between 1 to 100 nanometers. So how much is 100 nanometers? It's, if you convert into microns, it will be 0.1 micron. So from 1 nanometer to 100 nanometers, if any dimension is in this region, then we call it as a nanomaterial. So again, what do we mean one-dimensional nanomaterial? So someone raising hands, is there any problem? I can see 2 people raising their hands, right? If there any problem, please use chat, or like you can unmute your microphone and tell something. If there isn't, then I will move forward. Yeah, please go ahead. What's your problem? I still can't hear you. You can use chat. You can write your problem there. And I will continue. I guess we have a lot to discuss, right? So, please. If it's not, I will continue then. Yeah, so sorry, it's not clear actually. So in this one-dimensional nanomaterials, so my two axes are, for example, if I take my x and y, so it will be my the circumference, right? Yeah, it will be my circumference, and my z-axis is my length. And again, my circumference, my total circumference, for example, to measure the circumference, we take one dimension as radius r. So one quantity r is enough to define my x and y axis, right? So if my r is in nanometers, what happens if my r is in nanometers? So that means my x and y are in nanometers, right? So it lies between 1 and 100 nanometers. Okay, voice clarity, right? So I guess it should be okay now. Yeah, so all two dimensions are not in are in nano regime, and one dimension is not in nano range, right? So like for example, if my length is in more than 1 micron, so for example CNTs, right? If I'm using CNTs, then CNTs have very long length, right? For example, it can even reach to a few centimeters or few right? So then the length is not in nano regime. Then you call this as the one-dimensional nanomaterial. Now what about two-dimensional nanomaterials? Two-dimensional nanomaterials are nothing but if two of these dimensions are not in nanoscale, right? So for example, if I take a thin film, right? So if I take a thin film, then my x and y are not in nano range, but my thickness, which is t, we call it as a t, my thickness is in nano range. So the thin films have, for example, if I take the thin film of 50 nanometers, so which we actually see in some MOSFETs and JFETs, in new technically formed transistors, you can see there the thickness is quite low, right? So that is one thing. Now what about three-dimensional nanomaterial? Now coming to zero dimensional nothing but those all three dimensions are not in, are in nanoscale, right? So for example, the quantum dots, though for example if some people who have studied metallurgy, they can relate to granular piston zones or GP zones during solidification. So they start with the nanoscale. Yeah, so whose all the dimensions, right, it lies in nano regime. Then only you call this as the zero-dimensional nanomaterials. There are so many types. There are quantum dots, there are buckyballs, there are Buckminster fullerenes. So is there like eco or what? I know, can you in nanoscale, one dimensional, that means only one dimension is not in nanoscale. And if I'm talking about two dimensions, then two dimensions are not in nanoscale, and finally the three-dimensional, where all three dimensions are in nanoscale. Again, why do we call three-dimensional as three-dimensional nanomaterial? Because even though the three-dimensional material, every dimension is not in nanoscale, the micro constant of it. What do I mean by micro constant? So, for example, if I take ceramics, right? So the ceramics might contain not ceramics. Let's take composites, right? So there is a base material, parent material, and there is an additive, right? So for example, the base material I can take as steel matrix, and which is not in nanoscale. If I'm taking a big block of steel, which is not actually in nano range. So in that material, if I imbued my fibers like CNTs, carbon nanotubes, or carbon fibers, or like any other polymer fibers. Okay, resound. Okay, so it's echoing, right? Okay. Understood. Yeah, so again, there are different again different take dimensions. For example, there are different atoms for a, so for example, if I take copper atom, like it will have lattice parameter angstroms, so that dimension is different, right? So there are a lot of other things. Now, moving on to the next one. So it's just the introduction to nanomaterials, that's all. Right? Now, the left one shows the leaf, and in leaf you have chloroplast. Sorry, you have chlorophyll and then you have chloroplast. Now how do they work? Right? So whenever you have a small material, for example, if my surface got reduced, so this, for example, it is in 10 nanometer range. Now if a photon hits it, now all the surface electrons, right? So whenever you have a surface, so there is like unsatisfied bonds, right? So inside the material you can have atoms and they are perfectly bonded with each other, right? There is no breakage of bond when I am talking inside the material. Now what happens if I am talking outside the material? So when I am talking about outside the material, some of the bonds are remain untouched, right? So there is this dangling bonds. We call them as a dangling bonds in physics, and sometimes there are different names to call it. For now, you can take take it as a free bonds or dangling bonds, right? So the above one, bonds are not satisfied. So let's say this is my surface, and my surface bonds are not satisfied. So if my surface bonds are not satisfied, then what happens? So the first thing that happening is the strain, right? So when an atom is at equilibrium, how it is at equilibrium? So when you go to quantum mechanics, there is this potential well, right? Where the energy of the atom is minimum, and now when it is minimum, it forms all four bonds. For example, if I take silicon, right? If I take the silicon atom, so it should form four bonds, right? So the coordination number is 4, so it should not the coordination number. So it should form four bonds around it. Then only it can attain. In basic chemistry, there is this thing called the octet electronic configuration, right? So that's how it is more stable. Now, what if I try to break this bond? So one of the bond is not satisfied. Then that means some energy is being unsatisfied. So it will not be at the equilibrium state, which is E naught. So then what happens? So there is this accumulation of energy, n equals to 1 to n. Let's say this is as EI. So there is this accumulation of energy, right? The unsatisfied energy, or people call it as extra energy. So that energy is nothing but called as a surface energy, right? And that is very in layman term. You cannot actually you can prove it, but it depends upon the crystal structure. So which phase we are trying to cut it. So let's take a simple example. This example is a simple cubic, right? And again, if the people are from metallurgy background, they can easily relate. But again, I will explain things. So there are few basic crystal structures, 7 crystal structures, and there are 14 Bravais lattices. And what do you mean 7 crystal structure? The crystal structure is nothing but the smallest, the building block of a material, or the building block of a grain, right? Yeah. So if I have a grain, so if I see any material, in material there are a lot of grains, and that is why we call it as a polycrystalline material. So there are a lot of grains, and what do you mean by grain? Inside a grain, the arrangement of atoms is symmetrical, right? So for example, in a grain, you can see the atoms are arranged like this, and these the intersection points are where you see the intersection points. So there the atom lies. So these are facing this direction, and in next grain, you can see these atoms may face in some other direction. So that's where the topic comes, the low angle, high angle grain boundaries. So let's not talk about that. For just simplicity and explanation, this is what we mean by grain. And inside grain, you have the simple arrangement of, I shouldn't say simple arrangement, a periodical arrangement of atoms in one direction, or you can say the atomic planes are arranged in one direction, right? Now, if I am talking about a simple cubic, so if this is my cube, all the corner atoms are being occupied by atoms. So this is what I mean by simple cubic. Now, what about FCC, which is the face center cube, right? So I have atoms here at the corners, not only at the corners, but you can even see the atoms sitting at face centers. Right. So not only you have atoms sitting at corners, you even will have the atoms sitting at face centers. Now what about the BCC, or you call this is CC, which is face center cubic, because atoms are sitting at face centers. And the next one you have is the BCC, which is we called as a body center cubic. Now, the name itself suggests it's simple. Again, all the corner atoms are taken. Apart from corner atoms, you will have a center atom. That's all. These are the basic crystal structures. You can even go for HCP. Like it's little bit complex. You can just look into it, or I can explain it in later sessions. It is not required here. So for example, I'm only going for simple cutting wise. So let's even draw the simple cubic here. Let's say for example, let's take a hypothetical atom. It has simple cubic. The simple cubic is very rare to find. You can only find in polonium. So polonium will show the simple cubic crystal structure. Let's say I have an atom here. It shows it has simple cubic crystal structure. Right. Now what I'm trying to do is, now these atoms are like very happily arranged in some direction, right? And if you see my simple cubic, all atomic bonds are satisfied. Now, what I'm trying to do is, I am trying to cut the simple cubic along this direction. Right, I'm cutting it in half. Then, if I see it from top view, these atomic bonds are not satisfied. Right. So each atom is losing one bond. So each atom is breaking a bond. So then it is straightforward. So if I cut a simple cubic surface, how many atoms are there? I have 4 atoms. How many bonds are being broken? 4 bonds. So what is my surface energy? Or I shouldn't say surface energy of what? Surface energy of this crystal, right? So surface energy of crystal is the excess energy or the energy that's not being satisfied, right? Then that will be equal to summation of energy of single bond, right? So let's say this is A atom, then it should be AA bond between AA atom, right? Summation of AA atom times summation runs from 1 to 4, which is again every atom is assumed as identical, which is identical. Then this will sum up to 4 EAA. So this is my surface energy of crystal. So this is what is called as surface energy of crystal, right? Now what about FCC? FCC is not very straightforward, which I will discuss in later sessions. I will just show it. It will more or less look like this. So again, there is like three bonds are being broken per atom. So that will again result in different value, which is not straightforward. So let's see it in next sessions. Let's leave it here. Now coming to the surface energy part. Now because of this, again, loose or the unsatisfied bonds, and wherever there are unsatisfied bonds, then there is some electrons there. So a bond is formed between two electrons, right? So electron from one atom and electron from another atom will hybridize. In simple terms, they just form a bond, right? If you go into depth, you will have a hybridization and many other things. There is a degeneracy, so let's not talk about that. So when these, in simple terms, electrons are close together, then they will form a bond. Now, if these bonds are not satisfied, then there is one electron from each atom that is being remained. Now if I am talking about metals, then there is theory called free electron theory. Nothing but in metals, the electrons are freely moved, right? They are just a soup of electrons which are just moving around in the crystal structure. That's all. Now, so coming to this part, all these colors are emitted by a single material, right? So for example, gold nanoparticles. And again, someone asked what is particle, right? So let me give like examples for that also. So people are mostly confused with particle, grain, and you have crystallite. Now these two are very straightforward because they are these two are related, whatever concept whatever context you take. So context is nothing but whatever situation you take. Now these two are not related when compared. It depends on context. So what context you are speaking. So for example, if I am talking about material, let's say if I am talking about material, then my particle can be grain, right? If I am talking about in material context. Now if I am talking about in powder, then my context will change. So my powder particle is a single, or you can say a powder particle is nothing but the entity which has grains, right? Now this powder particle will contain grains. So actually if I take a bulk material and if I see under microscope after etching, you will see grains. Now if I take a powder particle and it has so many number of grains, right? Now if I am talking about nanoparticles, so again the nanoparticles will not have grains. Why? Because it is a single grain, right? It is just if I am talking about nanoparticle, it's just a collection of atoms. It will become itself a grain, right? So particle, grain will depend upon what context you are using. So it is not just straightforward. So if I am talking about powder particle will have different size depending upon the particle size distribution. So in powder, some particles may be big, Maybe some particles may be small, so some particles will have a lot of grains, some particles might have very small number of grains. So it depends upon what context you are using, right? Now, next moving to grain. So grain is nothing but, again I have said before, a grain has the periodic arrangement of atoms, right? So for example, this is my lattice. This is a chain of atoms. Now, if I take my grain, then these intersection points are my atoms. So let's say if I try to increase this, if I try to draw, then this will become my plane. A plane consists of atoms, right? And if I stack these together, then I will have a crystal structure. So if these stacked planes are like set in particular one direction, so all these planes are stacked. So this is plane 1, this is plane 1, plane 2, plane 3, plane 4, and so on. All these planes are stacked together and they are kept in one direction, right? So for example, it is x1, y1 direction, right? So one particular direction or north direction. So if my voice is not clear, please bear with me. Tomorrow I will do something about it. Okay? So let's just, I cannot like drag this meeting for so long. We will have the next meeting. I will have some make some things so that this thing will not happen again. Okay? Now all these planes are stacked in some direction, right? So then we call it as one grain. Now, for example, what happens if there is some distortion from these atoms to these atoms? So for example, what if my plane looks like this, right? If my planes are stacked like this, up to this the atoms are facing this direction, but here the atoms are facing, are just slanted, right? We call it as a slant. That means this is my direction, just a little angle like d theta, a small angular difference, right? Yeah, if we have a small angle difference, then this will be my crystallite. So in pure, again, crystallite. So it is coherently scattering domain, right? Now my crystal voice should be clear now.
Yes, sir.
Yeah, thank you. So coming to crystallite, so what do you mean by crystallite? Crystallite is nothing but coherently scattering domain, right? That means, see, so plane should be perfectly, right? So atoms should be perfectly aligned, then only you call it as a periodic arrangement. If there is no periodic arrangement, right? If there is no periodic arrangement, then what do you call them? So we cannot call it as a grain. Then if there is some distortion between these two grains, so these are some group of atoms, let's say A1 and this is A2. For example, there is some distortion, not a lot of distortion such that it will change the whole grain itself. There is only some distortion, then we call this guy as a crystallite. Why? Because there is a perfectly ordered arrangement. There is no distortion at all. Every lattice is same. So for example, this is my atom, and it is sitting at 1.4 angstroms, for example, I should say 1.4 angstroms. The other atom also should sit at 1.4 angstroms, right? If I'm talking about simple cubic, then it should look like this. So 1.4, again 1.4, 1.4, 1.4, 1.4. So every lattice parameter is nothing but the distance between two atoms, right? Or the bond length, you can even call it as. So in layman terms, it's just the distance between two atoms, right? It's not correct, but you can say it was a bond length, right? If the bond length is 1.4 angstrom, everywhere you go, it shouldn't change. Then only you call it as the perfectly periodical arrangement. Periodically means you can go anywhere and you see the same symmetry, right? Then only we call it as a periodical arrangement. So wherever you see there should be a perfect periodic arrangement. There shouldn't be 1.5 angstroms anywhere. Then only call this set of atomic planes, collection of atomic planes, called as crystallite. Now, a grain is made up of like 10 to more than one crystallite, right? If even the whole grain itself has perfect arrangement, then that is good. If it is not, then you have more number of crystallites in there. So that is the difference between grain and crystallite. So crystallite, in diffraction terms, it is a coherently scattering domain, or in periodical terms, all the atoms are periodically arranged, perfectly periodically arranged, right? Now grain is nothing but the collection of planes that are facing one direction. I'm not saying any distortion between planes. So please have your definitions clear. So this is by far the definition I have went through. Yeah. Now coming to this one, so I hope I have cleared the particle, grain and grain crystallite differences, because the metallurgical people always deal with this confusion. What is powder particle? What is the difference between the grain, crystalline and powder particle? Because people do X-ray diffraction technique, we will face this crystallite. So we used to calculate the crystallite size. Then there is this confusion. Oh, then if I have a grain, then how do I go to crystallite? If I have crystallite size, then how do I go to like grain? How do we differentiate these two terms? Yeah. Now moving on to this gold nanoparticles. Here you can see different colors, right? So you can see red, light red, yellow, green, light blue and sky blue, right? Now all these are like bottles contains a suspension of gold nanoparticles. So everything is gold there. There is nothing another material. So how is this phenomena actually happening, right? We can see different colors of the same material, which shouldn't be possible, right? We are not painting the gold material, gold nanoparticles, right? Now how is this happening? We shouldn't, like, for example, if you see an iron, it should have a shiny surface. If you polish it, you will get a shiny surface. You will not see violet color, right? Or you will not see a black color, right? If it get rusted, then it might get change its color. But you shouldn't see different colors, right? If, for example, if you see your phone charger, it should look white, right? Mostly white or white in color. It shouldn't change its color, right? So how is this happening? The same material, but it shows different colors. So the answer for this is, you will see this term everywhere. Like you will see this, like for most of these sessions you will just see this term. So I'll just explain it here. Surface plasmon resonance. So please bear with me. I will explain turn to turn. What do we mean by surface? Surface is nothing but the boundary between any two things, right? So the boundary between, so for example, if I am talking about a metal rod, right? So this is my metal rod. Then my surface is the boundary between this metal rod and air, right? So there is the stoppage of my material. right? It is a boundary between two things. That's why we call it as a surface. Now, the next one is the plasmon. Again, what do I mean by plasmon? Plasmon nothing but, so you people know photon, which is wave energy, right? No, what is plasma, right? So for example, if I have electron here and my another electron here, so in these, and there is another electron, and these three are oscillating, right? So this is moving up and down, right? It is oscillating in this direction. First it will move up and then move down, more like sinusoidal wave. So it is oscillating at one position, and this is electron 1. And for example, if electron 2 also oscillate in the same direction with electron 1, and electron 3 also is oscillating in same direction as electron 2 or electron 1, and if I collect these oscillations, and we call it as a collective oscillation. So that means, so for example, a guy is there and another guy is there, so these are three people, so he is trying to jump, and same B is also copying him and C is also copying him, so all three are jumping. So the same goes for electrons. So when these three electrons are oscillating, then we call it as a collective oscillation. You can call it as a collective electron wave. For better understanding, like for simple understanding, you call it as a collective oscillation, right? And plasmon is nothing but the collective oscillation of electrons. So there are two types of plasmons. One, the electrons which are on the surface, right? As I have said before, when you have a surface, the bonds are being broken, right? When the bonds are being broken, so one electron is free. So these are surface electrons which are free, right? So these electrons can have different frequency. And what about the bulk plasmons? That means the electrons inside the material. So the electrons inside the material, these can also oscillate. So for example, if I give heat energy, so if I try to heat the material, then electrons will oscillate, right? They will vibrate. So the same goes here also. So there are two types of plasmons. One is the surface plasmons, which are the free electrons on the surface. They are oscillating. The collective electrons are being oscillating. Now what about the bulk plasmons? That means the electrons inside the material are oscillating. The collective oscillation of electrons inside the material are called bulk plasmons, and the collective oscillation of electrons outside the material or on the surface of the material are called surface plasmons. So our two terms are clear, right? The free electrons which are on the surface, when they are collectively oscillating at a particular frequency at a particular phase. So every electron is oscillating, for example, at a single frequency f, right? Then I have surface plasmon. Now what is resonance? Resonance is nothing but oscillating at same frequency. So for example, if I take for example, I have a tuning fork and I have another tuning fork. So if I oscillate it at 10 Hz, and if I oscillate this guy at 10 Hz, so these two have same frequency, right? Or if I have one another tone like this, then if I take this guy near to this guy, then this guy will also oscillate at 10 frequency. Mostly, not for the total part. For example, the first instance. So then these two are oscillating at a single frequency. Then you call it as a resonance. Now, going on to this, let's say I have a nanoparticle, right? A nanoparticle has the surface atoms which are not being satisfied, and that means I have surface electrons. So now if something falls on it. For example, light energy. It can be photon, light energy, right? So light is made up of photons. It can be UV or it can be like violet, red color, anything. Now, if I try to drop light onto this nanoparticle, so this light has 7 colors, right? Observe. Now each color has certain frequency. F1, F2, F3, F4, F5. Each color of light has certain frequency. Now, when this mixed frequency falls on the surface, they will try to oscillate electrons, right? So this oscillation matches with if one of the oscillation, right? For example, if these are added onto the electrons, so these electrons will absorb that energy and they will oscillate. So if that oscillation has a frequency lying, so for example, light energy of h nu is called on a nanoparticle and the electrons are oscillating and that frequency is f1, then that will be violet. And this oscillation will depend upon the particle size. How? Again, if my particle is very small, then I have large number of unsatisfied bonds, large number of atoms on the surface. If my particle is big, then I have less atoms on the surface. If my particle is very large, which is in micron, then I have even less atoms on the surface, right? The smaller the particle, the more atoms are outside, the less atoms are inside, right? Here you have large number of atoms are inside, and here even more atoms are inside, right? Then that means there are more free electrons. If there are more free electrons, then there is more oscillations, and these oscillations have particular frequency. So it all depends upon what frequency these electrons are oscillating. If they are oscillating in F1 or F2 or F3 and F4, if they are operating at F1, then they emit violet color. So the same goes for here. So the gold nanoparticle, everything is gold nanoparticle, but the size difference. And because of the size difference, you have the number of surface atoms, the number of distribution of surface atoms is different. If you have a large particle, then you have less number of surface atoms. If you have a small particle, then the more number of surface atoms are there, then these atoms have dangling bonds, that means the free electrons, and these free electrons will oscillate, which results in radiation. And they emit certain radiation, and that radiation will depend upon what frequency they are vibrating, right? And this frequency will define what color we are seeing. So that is why this term comes again and again and again, because it is used in everywhere to even distinguish nanoparticles. So how do you, for example, if you do not have any equipment to like distinguish a nanoparticle, then you will see, it is emitting this color. That means it is of high size. I mean, its size is bigger than when compared to this blue one, right? So it's just an initial guessing value. It's not like I cannot exactly say, oh yeah, this blue color has like 10 nanometer range distribution of nanoparticles. No, you cannot say that, but you can distinguish, like, yeah, the red one has the more size when compared to blue one, right? So that is called as surface plasmon resonance. I hope I am clear. If you people still have any doubt, you can just ask, or you can just chat in the session, right? Now, moving on to how these nanomaterials are available in nature. So that is one very intriguing part. Why? Because you can see this shell, or people call it as an abalone shell. Now why I am showing this? Because it is hard to break these shells, right? Now why? It depends upon the layers. So for example, if I take a shell, right, if I take that shell and if I try to cut it and see the cross section. So for example, if this is my shell, right, top view, and if I try to cut it and if I try to see the cross section, this is my shell, and if I try to cut it and if I try to see the cross section, you can see there are different layers. One layer is calcium carbonate, another layer are protein fibers, and again you have calcium carbonate, again you have protein fibers. It's more like a composite, right? It's not made up of single material. It's more or less like it's a composite, right? Now, calcium carbonate is hard, right? We all know calcium carbonate is hard, so it will give you the hardness. Again, these shells are all sometimes even a little bendable. Again, calcium carbonate is hard, so that means if you apply enough pressure, it won't bend, but it will break. So that is the difference between, you will come up again, the brittleness and ductility. Right, the ductile materials means you can easily elongate the material or easily deform. So if I take a steel rod, very thin steel rod, I can deform it, right? Deform it and make it straight. That means the ductility, it is coming from the ductility, right? You can easily deform that material. What about the brittle materials? Like rock, you cannot deform rock. The rock will instantly break if you try to deform it, right? Now that where this, now that's where this brittleness comes from. So there is one thing on ductility. The ductility means you can easily deform the material. The brittleness, that means you cannot deform, it will just disintegrate. Now, but these abalone shells will even have a bendable property. That is coming from the protein, right? So when these calcium carbonate and protein layers are stacked together, and these layers should be of in nano range. This layer is like more or less 20 nanometers. Then only this phenomena can happen. So that means we are having best of both worlds, the brittleness and the ductility, right? Then my abalone shell can be hard and also deformable, right? So that is the thing. Diamond is hard, you cannot deform the diamond, it will break because of its brittleness. And same goes for calcium carbonate stone, stones, rocks, and many other things. So that's where the brittleness comes from. And ductility, you can take steel rods, you can easily deform, you can easily mold, right? So that is the thing. But they are not hard, right? If you apply some stress or pressure, they will deform. They are not hard as rocks or diamonds. So abalone shell takes the best of both worlds, right? It has its own hardness and it has its own ductility, right? Now that is about, now where this is coming from, the stacking of nano layers. See, you have two-dimensional nanoparticles. That means my layer is not in 2 dimension, my layer is not in nano range, but my thickness is in nano range. So again, that's why you will have this hardness and brittleness. So that is the beauty of this nanomaterials. Now going on to this magnetotectic bacteria. Now there is very intriguing part of this magnetotectic bacteria is, see, you actually see this magnetotectic bacteria in, this is bacteria you see in some lakes and oceans. Okay, so what about these guys is, the intriguing part of these guys is, they cannot be, this magnetotectic bacteria, the best part about them is, they live in lakes. That is simple thing, okay? Now, they cannot go deep. So this is my lake, this is the surface of the lake. They cannot go deep, they will die. Or they cannot come to top, again they will die. So there is this little buffer zone where they will survive. So that is the good thing about the bad thing about magnetobacteria is they cannot live on surface because of the sunlight, they will instantly die. And they cannot live at the bottom of the sea, bottom of the lake. Why? Because they cannot sustain the pressure. So we all know, we have studied physics in 10th and 12th. So when you go down depth, so when you reach the bottom of the part, the pressure will be increased, right? The rho GH term, I guess everyone know, right? So the pressure at the bottom will be equals to P naught, which is the atmospheric pressure, plus rho GH, right? So because of the high pressure, this magnetotectic bacteria cannot sustain there, cannot live. And if it goes above, and because of the sunlight it cannot live there, so it should maintain that level, right? Now how it will do that? And the interesting thing comes from is the magnetic particles. You can see this is the magnetotectic bacteria, and you can see these dark spots, right? These are the magnetic particles, or you can say nanoparticles. You can see these are containing a chain of magnetic crystals, 35 to 120 nanometers in diameter. Right, you can see change of magnetic particles there. Now, how it will help? See, we know Earth has its own magnetic field, right? I mean, we have studied, we have know that, and Earth is not flat. Again, Earth is spherical, not perfectly spherical. It is more bulged at center. So again, sorry for the flat earthers. So Earth is not flat. For now, for this explanation, let's say Earth is not flat. Okay, Earth is spherical but bulged at center. So Earth has its own magnetic field. We all know that. So now, so at surface, if you try to see, or in the lake itself, so let's say this is my lake. This red dot is my surface of the lake, and this line is my bottom of the lake. Okay, now we know the Earth magnetic field will look like this. Okay, Earth magnetic field is look like this. Now you can resolve this magnetic field in two directions. Okay, so you will have, if you will take theta here, then you will have BR and BN. This is Earth magnetic field. I am talking about Earth magnetic field. So we call it as an angle of dip in many cases. Okay. Now there is BR and BN. Now these, okay. So I have the magnetic bacteria, and inside the magnetic bacteria, I have chain of nanoparticles, right? And these nanoparticles are magnetic in nature. That means they give response to magnetic field. Now, if I move if I move to the bottom of the ocean, then my BN is more dominant, right? Because of the curvature. So it will know which direction which direction the magnetic field is more, right? If you go bottom to the Earth's surface, then BN is dominant, and if you move above to the surface, then BR is dominant. That's it. So depending upon this resolving of this magnetic field, or the magnitude of this magnetic field at different depths, right? For example, if I take at depth of like 1 meter, then my BN is more dominant, right? So my BN is more dominant. Now if I move to the surface, that means the magnetic field is getting weaker and weaker, right? Still the BN is dominant, but the BR value is getting increased, right? So that's how these magnetic particles will align and will say, yeah, so this is the stage we should remain. Because if I move top, then again I will not survive. So Br value increases, it will not survive. And if Bn is too large, then again it will not survive. So this, the what do you call, the respective value in which the Br and Bn are taken. Again, it's from the genes and experience, the how the ancestors have been survived. So depending upon this, it will habituated and maintain that range, not too high, not too low. So this is one good thing about the magnetotectic bacteria. Again, how it is happening? It is happening because of these nanoparticles. Again, the next thing is the Earth magnetic field is very low. It's in microtesla. Whatever the magnets we see, it has very high magnetic field. But Earth magnetic field is in microtesla. So again, the next problem is the magnetic field is low. The magnetic field is very low when compared to a normal conventional magnet. So again, the problem comes. So how do you dictate this magnetic field? How do you get response from this magnetic field? Because if you have very low magnetic field, so for example, if I have a strong magnet and very weak magnet, right? And if I try to attract an iron piece, obviously my strong magnet will attract. My weak magnet couldn't. Why? Because of less magnetic field. So there is this problem. Again, the magnetotectic bacteria solve this problem by making the nanoparticles in nano range, right? So what happens to this when a particle becomes nanoparticle? There is this term called super para magnetism. So when a particle becomes a nanoparticle, it will attain a special kind of magnetic behavior, which is called as a super paramagnetism. Now there are two terms: super paramagnetism. Paramagnetism is nothing but it is weakly attracted to magnetic field. Right? It's not like ferromagnets, not like iron piece which is strongly attracted to magnetic field. It is weakly attracted to magnetic field. Now again, there is super. So super, what does that mean is, even if you apply a small amount of magnetic field, what do I mean? Even if you apply small amount of magnetic field, the magnetization will start to increase. Right, so this is how it look like. This is MH curve. This is magnetization. This is magnetic field or magnetic flux density or magnetic field intensity. Okay. Even if I apply small amount of magnetic fields, my magnetization will be. That means the particle is very responsive. So that is what this graph means. So even at small magnetic fields, I have large magnetization. That means the particle is very responsive to the magnetic field. So that's how by size of this nanoparticle, this response to small magnetic field is being mitigated. So the first thing is we need to have a nanoparticle. Right. If only I have nanoparticle, then only I can have super paramagnetism, which will give response to magnetic field, even small magnetic fields. Right. So that is one interesting part of this magnetotectic bacteria. Now moving on to this one. So the fraction of atoms, percentage of the surface atoms, and the next one is the dimension. Now what do I mean by this? Right?
Sir?
Yes?
Sir, super paramagnetism is only applicable for nanoparticles, sir?
Super paramagnetism, oh yeah, it is mostly applicable for nanoparticles because, yes, I will explain why. See, when you have, there is this thing, yeah. You know coercivity, right? So everyone knows coercivity. So there are two terms. One is the coercivity and the other one is the retentivity. Right. So what do you mind? I will explain this two times. So this is my magnetization and this is my magnetic field, right? The strength of magnetic field. Now if I try to, so I have a magnetic field, first I have a material, and if I try to apply magnetic field on it, so because of this magnetic field, the domains inside the material will try to align in one direction. So because of that, we will have magnetization. That means the magnetic phenomena coming from the material.
Hysteresis loop, right, sir?
Sorry.
Hysteresis loop,
Yeah,
right, sir?
yeah, hysteresis loop. Yeah. So when I do this, now because of this magnetic field, my magnetization first will increase. It will reach the maximum value. Above that, it will not. So and then if I try to remove the magnetic field which I was applying, so this will drop and it will cut my y-axis here, and this is we call it as a retentivity, right? Now I have this M sat. Now this is my M saturation, the maximum value, and this is my retentivity. Now if I try to apply the magnetic field, reverse magnetic field, such that if I want to make this magnet completely non-magnetic, then I have to apply a negative magnetic field, that means in opposite direction. It will reach a value, it will reach magnetization as 0 and will cut x-axis at this point, and this we call it as a coercivity, right? I mean the amount of magnetic field that must be applied to a magnetic any material to make the magnetization 0. So that is called as a coercivity, and this is called as BR. Many people call it as a residual magnetization. That means the magnetization which is remained after removing magnetic field, or some people call it as a retentivity, remanence. So it depends on what term you are using. All are same. So nothing but this guy. Everything is same. Yeah.
Sir, paramagnetic material also have a magnetization value, sir?
Yeah, I'll come to that. Just give me a second. I'll come to that.
Okay, sir.
Yeah. So ferromagnets actually have this retentivity or BR, remanence or residual magnetization. The paramagnetic materials will not have the M residual magnetization. M residual, I mean the remaining magnetization. So paramagnetic materials shouldn't have. Ideally, they shouldn't have. Some might have depending upon the domains there in the material. So most of the paramagnetic materials will not have M residual magnetization. The residual magnetization is actually more seen in ferromagnets because it is again deep level. There is this term called exchange interaction. I shouldn't explain this. It is very high level for this course. So because of that exchange interaction in ferromagnets, even though if you do not apply magnetic field, you will have M residual. If you remove the magnetic field, you still have the magnetic field inside the magnet. The magnetic field creating property inside the magnet, or you call it as a magnetization. Now, for paramagnetic materials, if I remove the magnetic field, this M saturation, this M will go to 0 for perfectly paramagnetic material, right? Now, what is happening with super paramagnetism? Let me write it for paramagnetic. So, in paramagnetic, you will see a small value of this. You can see a very small value, like, yeah, it will more or less look like this. A very small value. In some paramagnetic particles, and most of will not have. So this is about ferromagnets and paramagnetic material. Now moving on to a question on why nanoparticles shows the superparamagnetism. You can see again coming to this graph, you will have Hc coercivity and you will have grain size. Right. Now, or you can call you just put it as grain size. Now first the coercivity, if I decrease the grain size, that means, so this is my large grain, then I have domains like this. right? Now if I try to decrease the grain size, the coercivity value will increase, right? Why? Why? Because I have domains in one direction. So if I try to decrease this size, then what happens? The number of domains will get decreased. So this coercivity value will increase. That means if I remove the magnetic field, applying magnetic field, this will remain same. They will not just cancel out each other, right? They will just remain same. That means this value will increase. Now up to a point, we call as critical point 1. That means you will have mostly, sorry, let me draw it again. Yeah. So very small domains which are facing another direction. So you will have maximum HC value here, and then it will start to decrease. And at a particular point, it will reach 0. And that point is called as critical point 2. And that size is called less than size, and I mean left to this, you will get super paramagnetism. Now, how? Again, the next question is how. So, in superparamagnetism, you have very small grains. That means you have single domain. So you have here you have a single domain, but the value is getting decreased. Now you have a single domain, but the domain. So this domain has a value of M1, magnetization M1, and it's not like there is a single nanoparticle. You will have so many nanoparticles, right? At one place. For example, if I take so many nanoparticles at one place. Now, it has value of M1. Now, if I try to apply magnetic field, and because these domains are small and there are no any other domains which are opposing them, so these domains will align in a single direction. Right, so that's why you will have M value very high. Where is that graph? Yeah, here you can see. Sorry, I will draw it again. So in M versus H, even on applying small magnetic field, because there is no restriction from domain walls. See, here you can see when I try to apply magnetic field, these domains will try to align in the magnetic field direction, but these domains, they are not facing in that direction. If they want to try to rotate, there is this domain wall that's blocking them. So this domain wall will act as a restriction to the movement of alignment of these domains in a alignment of magnetic field. And because of this domain wall, they cannot move. That means you need more and more magnetic field to align them in one direction. So coming to here, you do not have that, because each nanoparticle will only have one grain. Not one grain, one domain. There is no domain wall. So they can easily align in certain direction. So that's why even on applying small magnetic field, your M saturation value will shoot up. Like it just shoots up to maximum value. Right. Now the next thing is, because these particles are very small, and also I have said you have this dangling bonds, the extra energy there is there, and even if you apply a little energy to them, right? For example, if I give some temperature, if I increase my temperature, then these will change the direction. Why? Because they already have this excess energy, and this excess energy must be contained in some form, right? For example, if there is first law of thermodynamics, right? If you do some work, there will be energy released. The same thing happens. There should be conservation of energy. Where should this energy go? So if I try to give some temperature to these nanoparticles, then that temperature, that energy, that heat energy should go somewhere, right? So that will go into vibration of atoms. So if an atom will vibrate, then that means the electrons will change their spin. If the electrons will change their spin, then the domain will change its direction. So the same thing happens. So if I give some even small amount of heat energy, these nanoparticles will change their direction, even if you apply magnetic field. So that's why we call them as super paramagnetism. So super paramagnetism is only mostly seen in nanoparticles, because they have very first thing small domains, single domains. There is no domain wall, so they can easily align. The second thing is the excess energy and the conservation of energy. So this energy must go, and this will increase the vibrations, and because of the vibrations, these domains will change the direction, and the magnetic field will get, and the M value will go down. So that's why we call it as super paramagnetism, and that's why we see this super paramagnetism in nanoparticles, not in any other particles. Because if I have, oh, what happened to this? Yeah. So if I have a bigger particle, then I have different domains in here. This will be looking this direction, looking this direction, and then we have this direction. Here you have domain wall. Even if I give some energy, and because most of the atoms are inside the material, they can easily accommodate, but the surface atoms cannot, right? So in nanoparticles, most of the atoms are on surface, so they need to take that brunt, that heat energy, right? So that's why you will see easily misalignment in nanoparticles when compared to this guy. So that's why we even have a Curie temperature up to which our magnet is stable, right? Even if you give temperature, it will remain stable. Why? Because all the brunt is taken by the volume atoms, not the surface atoms, right? So again, there is no domain, there is domain wall, so again there is a restriction of motion of this. So if I apply small magnetic field, they will not get aligned. This guy needs to align, right? He will not get aligned because of this domain wall. This domain wall is restricting him to move into this direction. The same for this guy. He cannot freely move because of this domain wall. It's like you are sitting in a room and I'm trying to move to the next room. You cannot move because there is a wall between them, your rooms, right? So the same thing happens with domains also. So that's why the small magnetic field will not do much thing to this one. But in nanoparticles, because there are no domain walls, and also the domains are very small, they will easily align to this magnetic field. That's why you will have this shoot of M saturation for smaller values, but not for this guy. For this guy, it will look like this. You need to give large magnetic fields. It's more look like this. Right? I hope I am clear why super paramagnetism is seen in nanoparticles. The first thing is the size, that means the domain size. There is no domain walls, so easy alignment. The second thing is the extra surface energy. The atoms will easily vibrate because of if you supply some heat energy, and this M value, magnetation value, will go down if you increase temperature. So if I draw M versus T, it should go like this, right? If my temperature is low, then my magnetation is high. If my temperature is high, then my magnetation is low. Why? Because higher the temperature, higher the heat energy, higher the vibrations, higher the misalignment, lower the M value. I hope I am clear. I'll move forward. If there are no doubts, if there are still doubts, you can ask or not, or I will move forward. Okay? Yeah, okay then. I'll move forward. If you still have any doubts, you can write in text, or you can just like at the end of the class you can ask, right? Any doubt, like it's not like you don't think about there is silly doubts, difficult doubts. Every doubt is equal. You can just ask me, I will give you clarification. Yeah. Now moving on to this gecko guy. Yeah, it is not good picture, I guess. I mean, even I don't like this gecko. So yeah. So if I take this hand and if I zoom it in, So this is how it looks like. And next thing is the surface atoms, right? As I have said before, so let me show how this term, you people have listened many times. When you decrease the size, the surface atoms will increase, right? How? Let's see that how first. Let's say this is my cube, right? Now these are my surface atoms. Okay. Now these are my inside atoms, the volume atoms. Right. Now, if I try to break this guy, let's make it half. Okay. Let's make it half. Then what happens? I have two smaller cubes. Now, what happened? These surface atoms are same. These guys are also same. But there are two new surfaces that has formed. Right? You can see here you have S1, S6 faces, right? Cube has 6 faces. You already have 6 faces, but you have 2 new faces. That means you have extra surface that has been created. Now, again, what does that mean? Extra surface means extra bonds being broken. That means extra surface energy. So the surface atoms has increased. Now again, what I'm trying to do is I'm going to cut these two guys into again halves. So again I will have 4 cubes. Again I will have 4 new surfaces. Right. So each cube will give 2 new surfaces. This guy will give 2, this guy will give 2, this guy will give 2. So it is 2 to the power 4. Now how was 2 to the power of 4? It's 16, right? Yeah, it is 16. Now again, if I cut these guys into half, what will happen to them? Right? It will create 4 more surfaces, and this value will go on increasing. That means you are cutting the cubes, that means you are breaking bonds. Remember this, whenever you are trying to create a surface, whenever you are trying to cut a material, you are indirectly trying to break the bonds, or it's more directly, but just for understanding purposes, you are indirectly creating a new surface. That means you are breaking the bonds, right? That means you are indirectly creating excess energy, right? There is that excess energy still there, just like I have mentioned before. When is the atom is stable? When atoms are stable, when it follows the octet electronic configuration. If they are not in octet electronic configuration, then they will try to react with other elements and get electrons or share electrons to get octet electronic configuration. If you try to break the surface, that means you are breaking a bond. That means they cannot get or share that electron to attain the octet electronic configuration. That means they are, so this is my equilibrium energy. That means we are a bit higher in energy terms. We have excess energy. So that is what it means. So the more is the surface, the more you will have surface atoms. Again, how you will get the high surface? You will get the more surface area when you have when you cut the material into smaller and smaller and smaller and smaller pieces. Right? So there is this confusion again. Sir, you have a small sphere, you have a big sphere. The surface atoms on smaller sphere, you count it, you have counted it. Let's say that number is 10 zeros. Right? 10 zeros. You have counted on this guy. You have surface atoms of 2 times of this 10 zeros. Yes, the surface atoms are increasing, but what about the volume atoms? What about the fraction? So the surface atoms to the volume atoms, right? The volume atoms are so many, your surface energy is being dominated. It's not even there. People are not even seeing it. Here, because of this volume atoms are decreasing, your surface atoms are being dominant, right? Because of this value, the difference is getting increased, right? So for example, E naught. So again, I will explain more clearly why I am explaining this. Even I had this confusion. The smaller has less number of surface atoms, bigger has more surface atoms. Then why are we saying that the smaller particles will have high surface energy? So the thing is, so this is my surface well, this is my equilibrium, this is the surface energy, the excess energy. Now, if I have a small particle, if I have a very big particle, so let's make it comparable sizes. Let's say I have a small particle, let's say I have a very big particle. Now, the atoms which are at equilibrium, here it may be 10 to the power of 10, and the number of atoms on the surface is 10 to the power of 2, right? So atoms on the surface is 10 to the power of 2, atoms inside the material are 10 to the power of 10. Now, the energy of each atom, right, minimum energy, right? So E naught will be 10 to the power of 10 plus, let's say 10 to the power of 1, okay, for simplicity purpose. Now excess energy from the atoms is 10 to the power of 1. So what is its summation? It will almost look like this, right? When you try to add it, so it's more like this guy, 1 plus 0.000000001. What is this value? It is 1.00001, right? So it is approximately equals to 1. The same goes here. Because this value is so large, this value is being diminished now. And because it is diminished, what about the energy levels? Now how does this energy levels look like? What is the total energy of the system? Now this addition will give me the total energy of system, right? What is my total energy of system? This is my E1, this is my E0. What is my total energy? My total energy will just lie here. So this is my E total. That means the system energy. So now you can clearly see, because this guy is so dominant, our total energy of the system just lies above this guy. That means we are not stable but almost stable. It's like same not different. There is meme, right? There is same not different. So the same goes here. Because this guy is so dominant, he is being shunned, and the total energy of the system is just a little bit above this guy. That means we can say the system is almost stable. It's not like very unstable, it will burst anytime. No, it's very stable because it is very near to this guy. Now moving on to the nanoparticle. Now here comes the crazy part. Now this is my total energy, this is my base energy, this is my energy, right? Now what number of, sorry, now if I take a nanoparticle of like 50 nanometers, you can count the number of surface atoms and you can count number of atoms here inside the material. You can just see from here, these two values are comparable. So if this is 10 or there are 20 atoms on the surface, so is the value, yeah, here you can see if my dimension, the size of the grain or nanoparticle is being decreased, let's just stick with here. Let's not get involved anything. Let's just go with pure basics. Okay. you have counted this, the number of atoms on the surface, it is 20, and you have counted the number of atoms inside the material, and it is still 20. Now you can say, this is my E naught, and this is my E1, the excess energy of atoms. Now, what is my total energy, or the energy of the system? It is 20 times E naught plus 20 times E1. Now if I take half, it will be 20 times of E naught plus E1 divided by 2. That means it lies in between. Now this is my total energy of the system. Now you can see the gap, right? Here you can clearly say, yeah, my system is almost stable. There is nothing to worry about. But here, there is lot of excess energy there. Why? The total energy and the energy which it is stable, the difference is getting increased, right? What about if I try to reduce this particle even more? This even may increase to this one. So that is what happening here. So that's why we say, when we go to the nano regime or nano range, the energy of the system is continuously increasing. Why? Because the surface atoms are getting increased when compared to the bulk atoms, right? It's not like the count of surface atoms, it's the ratio of the surface atoms to volume atoms, right? So from here you can clearly say, yeah, from here you can see, because the volume atoms are so many, our total energy of the system is almost stable. But our surface atoms and volume atoms are so equally comparable, our total energy of the system is rising. That means our system is not stable, it is trying to attain stability, right? So what happens if I give some energy, then this energy will even increase. So that's what happening in super paramagnetic particles. Here you can see, because the energy is so stable, even if you give the thermal energy, that means increasing temperature, the energy of the system will only rise a little bit, right? Only will rise some bit, not to this way. It will rise. That's why you will not see the domain walls being changing their direction with increasing temperature, right? You know, for the Curie temperature of iron is almost above 700 degrees centigrade. So up to 700 degrees centigrade, it acts as a ferromagnet, right? So that means because of the magnetic, its bulk magnetic property, the thermal energy will not do much. But what about here? What about here? We already have so much excess energy. If I try to give much, even a little bit thermal energy here, our domains direction is being destroyed. So that's how you get super paramagnetism. That's how you understand why the nanoparticles have excess energy, because of the surface atoms. So that's why you say, yeah, the nanoparticles have high surface energy. How this is coming from? Because of the ratio of surface atoms to volume atoms. Please keep it in mind whenever, I don't know who are going to work or do research on nanomaterials, but if you have your definitions clear, you can do anything. So that is the main part of understanding any theory. So yeah, that's how the super paramagnetism comes. That's how people understand super paramagnetism in basic form. If you do mathematically, again there are a lot of things. So if you want to go in deep, you can. But for this course, this is like most easy part, right? You can write mathematical equations and say, yeah, with an increasing temperature, our domains are getting destroyed. So that is one way, but that is more complicated way, right? So this is basic understanding. Now again, coming to this cup. So the same thing. When they made this cup, they made it with nanoparticles, gold nanoparticles. So that's why when you just throw a light, you will see like this. When you put a light inside and the light comes out, so depending upon the size of the nanoparticles, they will emit different radiation, and you all know why it happens. It happens because of surface plasmon resonance, right? And if this material thickness, this cup thickness is very small, like the material they have used very small, then even the bulk plasmon resonance will also give some color. The bulk plasmon resonance will also uh, give some of their part to different colors, right? So that is why when the light is illuminated from outside, you see nothing. But when the light is emanated from inside, and because the light will travel from inside to outside, you will have this one because of the bulk, and you have surface plasma resonance. And depending upon the size of the particle, again I'll just go through it. Depending upon the size of the particle, you will have the surface energy, or the total energy of the system will be increased, and because of that increase you have more number of electrons, and these electrons will oscillate, and this oscillation will have certain frequency, and when some light falls on them, they will absorb some energy and they will oscillate with high frequency, and this frequency, if it is in visible range, then you will see colors. That's all. That is how you understand surface plasma resonance. If you want to go deep into it, absolutely you can go. So to understand more deeply surface plasma resonance, you need to understand the complex dielectric. So again, this topic is too much out of our course, so it's just for your curiosity. If you want to understand SPR, you need to first understand, I mean, more physically. If you want to understand, then you need to understand the study this, what do you call, just now I said, I forgot, the complex dielectric theory. Everyone know dielectric, right? So complex dielectric theory is given by this epsilon naught in capacitance we use, right? So permittivity. So from this you can study. Actually, when we use in capacitors, we just use permittivity or relative permittivity. It is a real value. But when it coming to this surface plasma resonance, we divide this into the real value and the imaginary value. Again, it is out of the scope of this thing. So let's not discuss. It's just for your curiosity purpose. If you want to understand more deeply, you can search it up. Complex permittivity, complex dielectrics. So that is about this guy. Yeah. Now moving on to this one. So sir hasn't derived this part, right? So he just mentioned for three-dimensional material our density of sets is like this. For two-dimensional, it will have like this, and there are humps, and you will have discrete values. Sir hasn't explained this. So what is the time now? It is 4. Yeah, 4:52. We still have 10 minutes. So let's wrap it up. Then I will. Do you want this derivation? How this graph came, or should I move to the any other topic, or should I start the doubt clarifying? Like if you have any doubts, or should I derive this? Okay then. Okay, then I will derive this part. Okay. It's easy actually. It's not that much difficult, you know. I hope you people have heard about density of states, right? So I hope you guys know density of states. So density of states is nothing but the number of possible eigenvalues or eigenstates that can be accommodated inside a certain volume. okay, or the number of states available per unit volume. So that is its definition actually, like physical definition. So in quantum mechanics you have k space and real space. Real space is nothing but our space, the length, breadth, width, direction. And when you do the Fourier transform, you will get k space. So just in simple terms, you will have L space, which is the real space, and then you have k space, which is imaginary space or the vector. Wave vector. You can call it as a wave vector space, or people call it as momentum space. It's just a mathematical relation, right? So if I have x, then if I apply Fourier transform, then I will arrive with k. That's all. I hope you guys know what is Fourier transform, at least. Fourier transform is nothing but demodulation of any function into sine and cosine waves, into sine and cosine function. That's all. If you have a function, you do demodulation into some trigonometric functions or sine and cosines. That's all. That is most basic definition of Fourier transform you can get actually. So when coming to vector space or the momentum space, the density of states is represented in momentum space. So it is g of k dk. So if I am talking about three-dimensional, in three-dimensional my momentum space can be represented with sphere. Okay. Then gk dk will be equals to, it's more like an integration, right? We are trying to integrate from 0 to r, okay, or k. Because we are taking sphere, so we are just integrating, we are just finding a volume of sphere, that's all. So it will be 4 pi k square dk, and if I divide it by volume, because the definition is that, then it will be 2 pi by L whole cube. Right, now again from Bohr's, or you can take from Einstein equation, E is equal to h nu. Right, now what about what is the kinetic energy? The kinetic energy is given by E equals to h cut square k square by 2m. Now h cut is nothing but h by 2 pi. K is more or less representing a momentum. Okay, is not just a p, momentum. P equals to mv. So that's how we represent. So h cut square k square. Now we know momentum can be represented as 2 pi by k. So that's why this 2 pi comes here. It will become h cut. So h cut square k square by 2m. So you substitute. You just differentiate this first. Then dE will be equals to, this is constant. It will become 2k dk upon 2m. You substitute this dk value here, then we will finally arrive with this whole mathematical jugglery. Just cancel out things, right? 2m by h cut square e 2m by h cut square whole power minus 1 by 2 e power minus 1 by 2 dE. Then if you do this jugglery, we do not want these all terms. We only want these two guys, right? E power 1 minus e power minus 1 by 2 will be give rise to e power 1 by 2. So this is my g of e dE. Now k and e can easily be relatable. So you just shift it to these parameters, k to e. So this is my equation. dE gets cancelled, so it will not get cancelled. It's just I'm taking a relation. Okay. We have to do integration finally. So my density of states will look like this. That's all. That's how you get this. Now if you want to try, you can try. Do everything same, but instead of taking sphere, you have to take a rectangle. Right? So, sorry, you have to take circle, not rectangle. You have to take circle instead of taking sphere in 2 dimension. You can try it, it's easy actually. See this, everything is same. The GK DK will remain same. Instead of volume you will get area, because we are dealing with 2 dimension. Instead of 4 pi k square you will write 2 pi k, right? So how do you calculate area of this guy? You will do, sorry, 2 pi k into dk, and my area will be 2 pi by L whole square. That's all. This is for 2 dimension. And what about 1 dimensional? 1 dimensional will be, it will be a line. It will not be a circle, it will be a line. Then my line should be what? dk, that's all, divided by 2 pi by L. Because only length is there, because it was area it will be square, and because we have length it will be just 1. And you do the integration, you will get, yeah, when you do the integration, this will guy have 1 by 2, this will guy have 0, the power is 0, that's why you have these steps, and this guy will have e power minus 1 by 2. Okay, and this will be done by solving the Schrodinger wave equation. I guess people who have done BTech, in the first year you will have physics, and in physics you must have solved Schrodinger equation, and not like complex one. You just minimize everything. We take V infinite. I guess you people have done this. Even in chemistry also you people will do, right? Here V equals to infinite, V equals to 0, V equals to infinite. The potential well problem. You have distance A, this is my origin, this will be A plus A by 2, this will be minus A by 2. You will have your psi function here at psi function at x. Again, it's not time independent, don't even involve time, just take time independent. That means it is only a function of x, not a function of t. So again it will become simplified. So yes, you will get with this, the energy values are discrete, right? We do not have time to derive that, or else we would have done it. So that's all for today's session, and in next session we will go, we'll talk much more about different types of nanomaterials and what are nanomaterials even more. So thank you for joining this session 1. I hope you guys will attend for next session if your people didn't get bored. So yeah, I will make sure it will be even more interesting, the session 2. So thank you for attending. If you have any doubts, you can ask, or you can leave now, or you can just text in chat if you are not comfortable with telling your doubts, or you can just ask by unmuting your mic, or you can leave the session. Yes, please.
Sir, just on the very